All right, so we're recording the session. I'm going to share my screen. Let me know if you can see my screen. Okay, so we're going to start with problem 10 tonight. So we left off with problem 9 yesterday, and we finished problem 9. So um, one of the things that I want to talk about before we do problem 10 is the central limit theorem, okay, which will help us do problem 10 and on. So what is the central limit theorem? So it's best explained by um, a diagram like this. So let me go over this quickly. And so try to follow this. It's a little bit of a complicated, you know, theorem, but I think once we do a simulation on this, that's what my experience has been, that it's best explained using a simulation instead of going into the conceptual detail. Okay, so so for example, let's consider. So I'm going to start off this with considering a population. So there is a population, let's say. So we have some data of a population, and let's say that that population is not normal. Okay, so it's not normal, and it has a mean and some standard deviation. So to prove to you that I have this population, I'm going to create one. Okay, so I'm just going to create a population. So I'm going to use, and you don't have to do this, so just follow, with what I'm doing. You don't have to learn this, and what I'm going to do is I'm going to go to the simulate option and then create a Weibull distribution. So you don't have to do this. So I'm going to create 1,000 rows, one column, and so let's now say this is my population. Okay, so I just created some random data, and here it is, and this is my population data. And to prove to you that it's not normal, have a look at this. I'm going to go to graph, I'm going to go to histogram. I'm just going to create a histogram on this. So do you all agree that this is not a normal distribution? It doesn't look like a bell-shaped curve, right? So this is not a normal distribution, not at all. All right, so what I'm going to do now is I'm going to calculate its mean and the standard deviation. Okay, so I'm going to calculate its mean and the standard deviation. And so here it is, and I'm going to write it down. Okay, so here it is, and I'm going to say my mean equals 1.4242. Okay, 1.4242, and the standard deviation is 1.4173. So 1.4173. Okay, everyone with me so far? Okay, so all I did was I considered a population that's not normal. I calculated its mean and the standard deviation, and here it is. Okay, and the population size is 1,000. Okay, now the central limit theorem says this. Now what I'm going to do is now consider, I just calculated this for our sake. Okay, let's just consider that we don't know this. Okay, so now you have to assume that you don't know the mu and the standard deviation. Just assume that you don't know it. Okay, I calculated these because of something we're going to do later. Okay, but for now, just assume that we don't know this. So we are unaware of what the mean and the standard deviation are. Okay, this is an unknown population. We do know that it's not normal. All right, so what we're going to do now is we're going to use the central limit theorem that says now what you do is uh, take many samples. Okay, so take many samples from this population. So I'm going to take 1,000 samples from this population, and say that my each of the sample size, I'm going to call it I'm going to call it say I'm going to call it n. Say I want to use 1,000, um, a sample size of 1,000. Okay, so here's the first sample. I take the first sample. of 1000. And what I want to do is I want to calculate its mean. Okay. Here's a second sample of 1000. I want to calculate its mean. And I want to do this 1000 times. This is the 1000th sample. And I want to calculate 1000th mean. Okay. Now, how is it best explained? By me actually doing it. So let me show you how I'm going to do that. Now what I'm going to do is I'm going to go to this option called sample here. I'm going to take one. Brian, you're kidding me. Are you kidding me? We had, so you see, I had to plan my I had to plan my trip tomorrow and host a session tonight to miss the Grand Slam. I thought you were playing with me or something, but anyway, that's good. That's awesome. Okay, so everyone with me so far. So what I'm gonna do now is I'm gonna take 1000 samples, and each time I take a sample, I'm going to calculate its mean. Okay? All I'm doing is from this population, taking a sample size of 1000. Oh, sorry, sample size. Geez, I messed up here. Hold on. I'm gonna take a sample size of 100, and I'm gonna do this 1000 times. So N1 represents the first sample of size 100, N2 represents the second sample of size 100, and we do this 1000 times. Okay, so is everyone with me? Is everyone with me here? Here's the 1000th sample of size 100, and I do this. I calculate its mean. So let's do this now. So from this population that was not normal, I am going to take 1000 samples, okay, 1000 samples of sample size 100 each. And instead of saving the actual samples, I want to save their means. So I'm gonna save their means. Each time a sample is taken, I calculate its mean and I save it. All right, so here we go. So here it is. So each row here in this column, each row represents the sample mean. This is, for example, here in this case, 1.5406 is the mean x bar 1. 1.4876 is the mean x bar 2. Okay, and I did this 1000 times, so I have 1000 means. Everyone with me so far? Okay. Here's the crazy thing now. All right, here's the crazy thing. So I just took 1000 samples. I calculated 1000 means. Okay, for each sample, I calculated a mean. And now let me calculate. You don't have to worry about if you're not following this, don't worry about it, because at the end the result is very simple. All you have to do is memorize it. But I want to explain it. I like to explain to students why it is what it is, and you'll see what I'm getting to. Okay. So now I have 1000 samples and they're 1000 means. Okay. Now let me calculate the mean of all these means. Let me calculate one mean for all these means. Okay. So I'm going to go to stat, summary stat, column, and I'm going to calculate this guy. I want to calculate its mean and the standard deviation. Okay, so here it is. Let me save it. But before I do that, let me show you what this distribution looks like. Okay, so let me show you what this distribution looks like. Did you see this? Isn't this remarkable? This is a remarkable result. So what just happened is I had a population that was not normal. You saw that it was not normal. I took out 1000 samples from that population, and each time I took a sample, I calculated its mean, and is represented by by this column here. These are each of those 1000 means. And then I created a graph of those means, and you can see that the means are showing that they are normally distributed. Okay. This is what the central limit theorem says. No matter what your distribution is, no matter what your population is, whether it's normal or whether it's not normal, If you take out many means of a sample size and you create a graph out of it, you will get a bell-shaped curve. Okay. Now, here's a remarkable thing. You see these results here? Take a look at this result. This is the mean of the means. This is this guy. I took out 1,000 samples each time I had a sample mean, and I calculated an overall mean of all those means, right? This X bar bar. I call it X bar bar because it's the mean of all the means. And which is this? X bar bar. Do you notice how close this is to the population mean? Did anyone notice that? Do you notice how close it is to this guy? It's almost the same. The mean of the means of all samples is coming out to be almost the same, right? So even if this was unknown to you, if this was not known to you, you could take out many samples, calculate means of each of those samples, and then calculate an overall mean, and you will actually find this unknown population mean. That's what this is saying. In other words, this is what you have to memorize. Under the central limit theorem, you have to memorize that the sampling distribution of X bar, sampling distribution of all these samples and their means, okay, is normal. This is the first thing you have to memorize, is normal. Second, you have to memorize that this X bar bar is approximately equal to the mu. It's approximately equal to the population mean. So even if the population mean is unknown, you can estimate it using this method. And then the third thing you're going to find is that this S here, this S, standard deviation of all the means, equals population mean divided by square root of n, which was your sample size. So for example, in this case, you expect your S to be equal to 1.4173 divided by square root of 100. 1.4173 divided by 10. So it should be close to 0.14, whatever. Okay. It should be close to 0.14. So let's see what we got. Let's see what we actually had. And what do we have? We have 0.1318. Very, very close to this, that what you expect. Okay. Yes, each time I took a sample, my sample size was 100. So I kept the sample size the same. Okay. Now, when I make the recording available, go over this one more time. Okay. When I put the recording up, go over this explanation one more time. But this is all you have to memorize. You have to memorize that the mean of the means is approximately equal to the original population mean. Okay. And the second thing you have to memorize is that the standard deviation of all the means here, it equals the population standard deviation divided by square root of n. This is all you have to memorize. And if you can memorize this, then you can do all these problems that we're going to do tonight. So let's now do a problem, and then you'll see it's actually very easy to apply. It's harder to understand this concept, but it's very easy to apply. All right, so let's do a problem, and then it'll make you feel better. So here's the problem. Okay, now in this case, notice that the problem is asking determine mu x bar and sigma x bar. Okay, now they're asking you find mu x bar and sigma x bar. This is the same thing as saying, the x bar bar and, the S that we just estimated. This is what that is. Okay. And here is the population data given to you. You see, this is exactly the population data that I just used to show you the example, right? The population mean is 84. So the mu is 84. Sigma is 9. And n is 81. Okay. Now, how do we do this problem? So we have to find this and we have to find this. The first answer is very, very simple. From the central limit theorem that we just studied, the mean of the means, which is the mu x bar, is simply just equal to the mean. So this guy is just equal to 84. Okay, remember I said you have to remember this. You have to memorize it. The second answer for sigma x bar is simply you take the sigma of the population and you divide it by square root of n. Okay, remember I asked you to memorize this as well. So this equals 9 divided by square root of 81, which is 9 over 9, and that equals 1. That is it. Okay, this is it. This is basically you just applied what I just explained, using a fairly complicated, you know, or what I explained to you was a fairly complicated concept using that simulation. Okay, but this is the way to solve this problem. The mean of the sampling distribution equals the original mean of the population, so it's 84, and the standard deviation of the sampling mean equals sigma over square root of n, which is the population standard deviation, divided by square root of the sample size that you're taking. So it's 9 over square root of 81. So it's 9 over 9 and it equals 1. Okay. And this is the way to do this problem. Any questions here? I think it's very simple. All you have to do is just memorize a formula and then, apply it. And if if you think you did not understand the concept, my suggestion is go over the, that explanation I just gave, the simulation I did to prove that this is in fact true. Just go over it a few more times and you'll understand it. Okay. Oh, X bar. So in this case, X bar, what they're saying is, remember from my drawing, remember I was taking many, many samples. I had N1, then N2, and then I took N1000, right? Sample. Well, each time I took a sample, I calculated its mean. Then X bar pretty much means that I'm calculating the mean. So X bar 1 is the mean of the first sample. X bar 2 is the mean of the second sample. X bar 3 is the mean of the third sample, and then so on. Okay, so overall, X bar is a distribution. It's a distribution of the means, of all the means that we just calculated, right? So X bar is a distribution like X bar 1, X bar 2, X bar 3, blah, 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 X bar 1000. Okay. Conrad, I'm not sure if I understand that question, but let me just go over this one more time quickly. And as I said, I think this will be best explained if you can just go over that first part where I went through a simulation again a few more times, and then you'll understand how I'm getting to this. But the answer to this question is, the question was, what is the mean of the means? What is the mean of all, of this distribution of the means? Okay. And we proved using central limit theorem and something that you have to memorize, we said that mu x bar, which is the mean of this distribution, equals the original mean of the population, which is 84. Okay, so is this clear? It will always be like that. And we'll do a few more problems, then you'll get used to it. Okay, great. And then we said the standard deviation of this distribution of all these means here, standard deviation of these means is equal to the population standard deviation divided by square root of your sample size. So the population standard deviation was given as 9. Your sample size was given as 81. So it's 9 over square root of 81, which is 9 over 9. So it equals 1. What that means now is that the mean x bar bar of this distribution is 84, and the standard deviation of this distribution is 1. Okay, so let's do a few more problems and then you'll feel better about this concept. All right, so this was problem 10. Now let's do 11. So the trick will be you'll have to figure out when you should do this calculation, okay? Because you won't have you're not going to be doing this all the time. Only when the question asks you about the sampling distribution. So let's see when it's going to do that. So suppose the length of pregnancies of a certain animal are approximately normally distributed with mean 125 and standard deviation 11. Okay, so the population mean is 125, population standard deviation is 11. Okay, this is the population data. What is the probability that a randomly selected pregnancy lasts less than 121 days? This is just like what we did yesterday. What we want, probability that X is less than 121. And you all know how to do that. So it's simply okay, if the center is 125, where is 121? On the left side or the right side? It's on the left side, right? 121 is less than 125, so it's here. Okay. And what are we looking for? Area to the left of it, so we're looking for this area. Do you all agree? Okay. So let's do this. So just like yesterday, I'm going to go to Stat, Calculator, and Normal. So I'm going to use the normal calculator. My mean is 125. Standard deviation is 11. And I want area less than 121. I hit compute and I get the area kind of like what I was looking for. And the probability under the curve is 0.3580. Okay. Any questions so far? I think this is just like yesterday. Nothing has changed. So it's fairly simple. Okay. Well, now, okay, now, how did I reach the cal? Sandra, can you ask that question? Do you mean how did I calculate this? Oh, the calculator is stat, calculators, and normal. Okay, so we went through this in detail in yesterday's webinar. So have a look at that where where I actually explained it in quite a bit of detail how to use this calculator. So that will let's see, this is the calculator I just used. And we also use the two options, standard and between. Okay. All right. So, but now the question is different. Okay. This is what you're going to have to figure out where what kind of question are they asking you? Well, now the question says, what is the probability that a random sample of 15 pregnancies has a mean gestation period of 121? Now, the question is asking not to randomly select one pregnancy, right? It's asking that what if you select a random sample of 15 of them? Then what is the mean? Okay, sorry, then what is the probability that X is less than 121? So in other words, what they're now asking is what is the probability that your and I'm going to call this, so remember the X bar distribution? So I'm going to call this, say, X bar, and I'm going to maybe make it look a little different. X bar is less than 121. Now your sample size here says 15. So N is 15. So tell me, what is X bar bar for this? Which is also called mu X bar. So can you tell me what is mu X bar for this problem? Just like what we just did, in the previous problem. Not 15, 120, 125. Kimberly, I think you meant 125. Original population mean. From the central limit theorem, mu X bar, which is also the X bar bar, is the same as the original population mean, 125. Okay? Is this clear? The mu X bar, the mean of the sampling distribution, is the same as the original population mean, 125. Okay, good. So for this distribution, this is now going to be normal with mean 125, but we also need the standard deviation. So what is the standard deviation for this? Which is the sigma X bar. What is that equal to? Not just that. First, let's go through the formula. What is the formula for this? Very good, Katie. Very, very good. It is sigma population mean divided by square root of n, meaning population standard deviation is 11 divided by square root of 15. Okay? Does that make sense? Vince says he's confused. So Vince, can you maybe can you tell me which part is confusing here? So here's what you have to do. Whenever you get a problem where sample sizes are involved, you have to do this computation. You have to find mu X bar. That's the same as the mu, okay? And then you have to find sigma X bar. That's the same as sigma over square root of n. And then the rest is just plugging in the values, right? Mu X bar is simply just mu, which is given as 125. And sigma X bar is simply equal to original sigma divided by square root of n. Original sigma is given as 11, and you divide it by square root of n is given as 15, right? And so you get the two answers. This you have to calculate, this guy you have to calculate, so let's calculate it. I'm going to do it in Excel because it's easier. So the way I calculate 11 over square root of 15 is I say equal 11 divided by square root of 15. And I get 2.8402. 2.8402. So I get 2.8402. How did I get 15? Well, 15 was given in problem B as the sample size is 15, right? So n equals 15. Yes. Here's the Excel equation. I said 11 divided by SQRT is a function in Excel that calculates the square root. SQRT of 15. Okay. Does that make sense? So the answer came out to be 2.840188. So it's approximately 2.842. All right. Now that I have found this, so I'm just gonna write it up here. Part one of the problem? You mean part A? Okay, I think there's a lot of confusion going on. So I'm gonna redo the whole thing. So just give me a second here. So try to follow this time. So I'm gonna start from scratch. All right, so here's the problem. So I'm gonna go step by step and let's see if we can do it this way. So the first problem said, what is the probability that a randomly selected pregnancy, just one of them, okay, is less than 121? And we did it the way we have been doing the problems so far in normal distribution. Now the problem is different. Now it says, what is the probability that a random sample of 15 pregnancies, right? So now they're talking about a sample. You've taken a sample of size 15, and they want you to find what is the probability that it has a mean of 121 days or less. Okay, so do you all agree that the problem says n is 15? Do you all agree with that? And if you don't, please mention so I can explain it again. Okay, so n is 15. We all agree on that n equals 15. Okay, now I said, no, 15 is not the number of pregnancies. 15 is the sample size that we've taken, right? So it's the sample size that we've taken from this population. So it's a little different than, yeah, okay, that's what you meant. All right, so we have 15, so n equals 15. And now I said, using central limit theorem, the two formulas that you have to memorize, we have to find mu x bar, which is the mean of the sampling distribution. And I said that equals mu. And so that is just 125. Okay, is that clear? Always the same, always the same. The mean of the sampling distribution is always the same as the population mean. So it's 125. Is that clear now? So automatically the mean is the same. Okay, good, great. Now, obviously, we have to find the standard deviation of the sampling distribution. So sigma x bar. And I said, using central limit theorem, which you have to memorize again, it's sigma over square root of n. Sigma is the original population standard deviation. So can I say that that is simply 11 over square root of 15? Right? So is this step clear? Always that, yes. Okay, and then I calculated that in Excel and I got an answer of 2.84018. Okay, so I have my new mean, and I have my new standard deviation. Okay, and what I need to find is I need to find the probability that in this distribution I get a value of 121 or less. Okay, so let's draw it out. Here's this normal distribution again. I said that the mean is simply equal to the population mean, so the mean is still 125. So you'll still have 125 here. And I want probability that you get an answer of 121 or less. Okay, so 121 is here. And I'm still looking for the same area, just like before. Okay. And so how do we do this now? The only difference in this problem is the standard deviation that you have to use. You have to use a different standard deviation. Now let's go to StatCrunch and do this problem. So I'm going to go back to Stat, Calculator, Normal, and my mean is 125, but my standard deviation is not 11 anymore. Okay, you have to follow this. This is very important. Okay. My mean is still 125, but my standard deviation is not 11 anymore. Okay. My standard deviation, what is my new standard deviation? Can you tell me what is my new standard deviation? Absolutely right. It is 2.84018, which is what I calculated here. 2.84018. So I'm going to type that. 2.840188. Okay. And I still need the probability that the value is 121 or less. Compute it. And now I get 0.0795. So the probability is 0.0795. This probability is the probability that if I took a sample size of 15, then what is the probability that the mean will be less than 121? Okay. So is this clear now? The only thing we did in this problem that's different than part A is that we had to calculate the standard deviation of the sampling distribution and use that instead of using the original standard deviation. Any questions? So Peter, as I just explained, what this tells you is this is a different problem, right? The problem said, what if you took a sample size of 15? What is the probability that the mean of those 15 sample size will be 121 or less? In the previous problem, you only took one case from the population, and you said, what is the probability that this one case is less than 121? But now you're talking about a sample. You're talking about you've taken a sample, and you're talking about what is the probability that its mean is less than 121, right? So these are two different questions that that we're trying to answer. Okay, that's what this is telling you. It's telling you that the mean being 121 or less is slightly less likely than you selecting one case and that being less than 121. Okay. Okay. This is what I did. Okay. So I typed 11. First of all, I typed equal. Then I typed 11. And then I said, this is the division sign. And then I typed sqrt, which is the function in Excel for square root. And inside sqrt, I typed 15. Okay. And this is how and then it gave me this answer. So if you just type this, it'll give you, Excel will calculate the answer for you. This is the same as me calculating this. Okay, so as I said, the more, this will require some practice to get to this point. Okay. Now here's the trick. The trick is every time you read a problem that says, what is the probability that a random sample of some size, and then blah, blah, blah. Anytime you read this problem, you have to convert the standard deviation. Okay. So you always should convert the standard deviation whenever you read that the problem involves a sample. If it does not involve a sample, then just do the problem just like you've been doing so far. Yes, Chris, but that's only for me. Your problems are going to be different, so you'll have your own data. So, but yes, but in my case, it was 2.84018. Okay, let's move on and do the other problem. Okay, now look at the problem now. What are they saying? The problem now says, what is the probability that you increase you're increasing the sample size. What is the probability that a random sample of 48 pregnancies now is less than 121? So now your sample size has gone up. Sample size is 48. So what is my mean in this case? Can you tell me what my mean is? It's still 125. Very good. Same as the population mean. And what is my standard deviation in this case? Not just 11, Angie. Not just 11. Yes, 11 over square root of 48. Very good. I take the original 11. Here's the formula. 11 divided by square root of 48 because that's my new n now. Okay. And so let's calculate that. So just like I typed this, I'm going to say equal 11 slash sqrt and parentheses, and I'm going to type 48 and then parentheses closed, enter, and I get my answer is 1.587713. Thanks, Donna. Thanks for typing it there. I'm going to copy it from you. 587713. This is your new standard deviation now. First of all, notice that the standard deviation is lower than what you got in problem B. Can someone tell me why do you think it's lower? Why is it coming out to be lower now? Something has happened because it's lower. Not the population is the same. Something is larger, but not the population. Alfred, very good. Sample size has gone up. You have you have a larger sample. When you have a larger sample, you expect the variation to go down. The higher the sample size, the more precise your results should be. And so the variation should be lower. That's why it's down. So now what you do is, again, you have to calculate the same thing. You have to calculate x is less than 121. And you have to use this data now. So let's do it in StatCrunch. Again, 125 is the mean. The answer here, the standard deviation now is 1.587713. I still need the same answer. And look at what am I getting? 0.0059. 0.00. Even lower probability than this case. So Christopher, yes, but I think you have to be careful when you say that. So larger sample means more precise results, not lower results, but more precise results. When your results are precise, then your standard deviation is going to be lower, right? Because when you have a larger sample size, you're almost studying the entire population, right? As your sample size increases, eventually it reaches the population size, and then your results are absolutely accurate, right? So think of it that way. Think of it like as your sample size increases, you're approaching the population size. And when you approach the population size, then your results become more and more and more precise. So therefore, the variation in your results goes down, which is why the standard deviation is going down as the sample size increases. Is this clear now? Is this problem clear? It took a while, but I know, but I mean, this is a somewhat of a hard concept. Awesome, awesome. And again, just go over the first part of the lecture one more time, and then you'll understand this. Okay. All right. Now let's do this problem. The shape of distribution of time required to get an oil change is unknown. Okay. You don't know the shape. However, records indicate that the mean is 21.4, standard deviation is 4.7. Mean is 21.4. Standard deviation is 4.7. Right? To compute probabilities regarding the sample mean using the normal model, what size sample would be required? Okay, this is another thing you have to memorize. And the answer for this, for part A, is that generally you want the sample size to be at least 30. Okay, something you have to memorize. The sample size needs to be greater than 30. Okay, 30 is like a threshold. If you want to compute probabilities using the normal model, your sample size should be a little bit large. Okay, and by a little bit large we mean at least 30. So the answer to this question is that the sample size should be greater than 30. Okay, now you're gonna help me do this problem. Here's the second part of the problem. What is the probability that a random sample of N40 results in a sample mean less than 20? So N is 40. So what is the probability that you get X less than 20? So you're gonna help me solve this. So what is the first step? Step number 1. So what is the first step? What do we have to find? Absolutely right, Angie. Very good. We have to find the mean. So to be more precise, we have to find mu x bar. Okay. So what is mu x bar equal to? Very good. 21.4. Excellent. And what do we have to find next? Standard deviation bar. Sigma x bar. What is that equal to? Sigma divided by square root of n. Kathleen is absolutely right. Sigma divided by square root of n. 4.7 divided by square root of 40. Yes. Let's find what this is. And Robert has the answer already. Equal 4.7 divided by SQRT of 40. Okay, this is how you find this. The answer is 0.743135. So I match the answer from Robert. So I'm just going to copy it from him. So I'm getting, okay. Well, can we find this probability now? Center is 21.4. So 20 is going to be right there. And we want this guy. Okay, so let's do this. 21.4. So my mean is 21.4. My standard deviation is 0.743135, right? And what do I need? Less than 20. Is this clear? Are all these numbers clear? Okay, I hit compute and I get 0.0298. Let's go back a few steps. Can you specify which step here? Sandra, can you let me know which steps? Before the graph? I'm not sure if I'm following. So I think what you mean is this part here. Okay, so getting the new mean and the new standard deviation. I think it might help, Sandra, if you maybe go over the recording one more time, maybe. because this is something, as I mentioned, you have to memorize. Okay, unless this is memorized, there's no way to get the answers here, right? So I said that you have to find in part B you have to find a new mean. The new mean is always equal to the original mean, so that's 21.4. Then the new standard deviation is always equal to this formula here, and then you just plug in the values, 4.7 divided by square root of 40, and you get the new standard deviation. So whenever the problem involves the sample size, whenever the problem is giving you a sample size and asking you to find the probability, you have to do this conversion. And then and this is something you're going to have to sort of, I think you'll all understand it when you do a lot of practice with these problems. Then it'll make a lot more sense. Okay, and then we found that we need this, and then I drew the diagram, and I got my answer, and it is 0.0298. And that is the correct answer. Any questions here? Now that now that you're all getting used to these conversions, now if you go back and you review the first part of the lecture where I explain why this is true, it'll make a lot more sense. Okay, great. So let's move on. We're at the last two problems now. And in this problem, we are now talking about a different distribution, okay, and it's called p hat. And p is just a distribution called proportion, okay? So you know proportions, right? Proportions are just, the percentages, right? P hat. Describe the sampling distribution of p hat. Assume the size of the population is 20,000. So what they're saying is you have a population, big N, of size 20,000. And then what they're saying is your small n is 800. Okay, so you take a sample of 800. And out of the 800, you find that the proportion that you're interested in is 40% or 0.4. Okay, so in other words, x equals 40% of 800. Okay, so n times p. If I multiply n with p, 40%, so what do you get? So I can just calculate that. 0.4 times 800, I get 320. So this is 800 times 0.40 is 320. Okay. Everything clear here? P is just proportion. Why 40%? Because they gave us P to be 0.4. They said P is 0.4. So it's 40%. Okay. So this distribution is called P hat, which is the proportion. Okay. Now, what they're saying is choose the phrase that best describes the shape of sampling distribution of P hat. Now, this is something you're going to have to memorize also. You have to figure out if these two cases are true. Let's find the first case. The first case is that the sample size, small n, should be less than or equal to 5% of the population size, meaning your small n must be less than or equal to 5% of the big N. Well, let's find out what it is. What is 5% of 20,000? Right? The big N is 20,000. What is 5% of 20,000? Let's ask my calculator. It's just 1,000, right? It's just 1,000. So the question is small n less than or equal to 1,000? Is that true? Is it less than 1,000 or no? Yes, it is. 800 is definitely less than or equal to 1,000. And so this condition is okay. Again, you have to memorize it. Okay. Yes, Vince, it is less than. This just means less than or equal to, right? Either or has to be true. They both don't obviously they both can't be true. Either of the condition has to be true, either less or equal. In this case, it's less. Okay. The other condition that you have to test for is this condition, np times 1 minus p. So n times p times 1 minus p must be greater than or equal to 10. So let's test that. So I have 800, which is my small n. P is 40% or 0.40, and then 1 minus 0.40. I have to multiply all these. So this equals 800 times 0.40 times 0.60. Okay, 1 minus 0.4 is 0.6. Okay, and so what do we get? We get 800. Oops, I guess you can't see that. It's 800 times 0.40 times 0.60, and I get 192. Okay, so 192. And the question is so this whole thing, 192 is this left side. So is 192 greater than or equal to 10? Is that true? Yes, it is. So this is also okay. Chris, if I were to explain this, the concepts behind this, it would probably take another hour. And that is outside the norm of the course. But what you have to remember is what these two conditions are testing is what it's saying really is your sample size should always be small enough, not too large, small enough. Because if this sample size was very large, close to the population size, and then say your population is not normal, then your sample will not be normal, right? This condition is allowing us to use the normal distribution for any distribution, okay? So if your sample size was very large, then your sample size will be the same distribution as the population. Okay, that's the reason, conceptual reason behind this guy. The second thing here is, again, a test, and together with the first condition, what it's testing is it is saying, can we use the normal distribution to do the calculations when we have a proportion? That is all it's saying. See, this is why I said, yep, it's approximately normal because these conditions hold. If these conditions do not hold, then we cannot use the normal model to do calculations. Okay. Yes, Cheryl, I'll do the calculations in a little bit. Okay, so now that that's true, I have to tell you before we do this as to what is the mean and the standard deviation when you have p hat. So now that we said if both the conditions hold, then you can use a normal model. Okay, so because we said we can use a normal model, then we can use a normal distribution. So now that we can use a normal distribution, obviously we need a mean and we need a standard deviation, right? Because for normal distribution, we always need these two. So here's what you have to remember. Whenever you have a proportion distribution, then your mean is simply equal to p hat, whatever proportion you have in the problem. Like in this case, we have 40%. Then the mean of the normal distribution will be 40%. Okay, so in this case, it's going to be 0.40. And is this clear? First of all, is this clear? That the mean will always be whatever proportion they've given you in the problem. Okay, great. And then the standard deviation is going to be equal to this. Now this is a little bit of a formula. Square root of p hat times 1 minus p hat divided by n. Okay, so like for example, in this problem, my p hat is 0.40 or 40%. My n was 800, right? So I can just plug it in and get my new standard deviation, which is going to be equal to 0.40 times 1 minus 0.40 and then divided by 800. This is the same as 0.40 times, what is this 1 minus 0.40? It's 0.60 divided by 800. And then you have to find the square root. So now let's find this using Excel. Our friend Excel makes calculations easier. Yes. Well, not because it has to equal 1, but because I said 1 minus 0.40. Oh, you mean the total. Yes, the total has to be 100%, right? The total has to be 100%. So we said 100% minus 40% is 60%. Okay. So now let's find this. So I'm going to use I'm going to use Excel, and this is how I'm going to do it. So follow the steps here. I'm going to say equal. The whole thing is square root, so I'm going to say SQRT. And how about I do it stepwise? So just make it simpler for you. So I'm going to say first I'm going to calculate the inside, everything inside here. So I'm going to say 0.40 times 0.60 divided by 800. Is this clear? This is the everything inside the square root. So let's just find that first. Hit enter and I get 0.0003. Okay. Now I need to find the square root of this number. So how do I do that? I can just say equal SQRT square root parentheses. I'm going to click on this cell. So take your mouse cursor, click on it, and it puts A4. What it's saying is this cell A4, whatever A4 contains, whatever value it contains, find the square root of that. And then just close the parentheses here. There you go. Hit enter, and I get 0.017321. So I'm going to get thanks, Angie. Thanks for typing it out there. So that's the answer there. Now, what do we need? Well, we actually answered a few questions here. The question was determine the mean of the sampling distribution of p hat. Well, the sampling distribution of p hat, which is the the mu p hat, we said is simply just equal to the original proportion, which is 40%. Okay, so you just answered that question. Determine the standard deviation, and we just figured that out. We used this equation to figure out that is 0.017, so it's 0.017. Is this clear? Are these two steps clear? I think these are the most challenging steps here, really. Any questions here on this before I move to the last problem? I divided by 800 here. Remember I said the formula is p hat times 1 minus p hat divided by n. And so I plug in the values. P hat is 40%. 1 minus p hat is 1 minus 0.4%, which is 60%, divided by 800. 800 is my sample size. It's given in the problem. It's given right here. N equals 800. So it's just a matter of writing down the formulas and then plugging in the values. Oh, in Excel. Did I not do that in Excel? Oh, here it is. So first I calculated everything inside. So I said 0.4 times 0.6 divided by 800. And then I just took the square root of that. I could also have done it this way. You see, I can also do the whole thing in one step. Here's how I would do that. So This is everything inside, right? I can just put square root around it. So I can say sqrt, this. See that? I get the same answer. So you can do it in 2 different cells or you can do it in 1 cell. Okay. Any questions? All right, let's do the last problem. And looks like that's not good. The Cubs have given away two runs. All right. So how about you help me solve this problem? How about you guys do this problem, and I watch the Cubs? No, I'm just kidding. All right. So suppose you have a simple random sample of size n50. Okay. So n is 50. Okay. Is obtained from a population where big N is 10,000. Big N is 10,000. Okay. And whose population proportion is 40%. Well, that's weird. Same population proportion. So it's 40%. Okay. And describe the sampling distribution of p hat. Okay. So again, you have to do this checks, and I'm sure you can do this now, and you'll find that it is going to be approximately normal. Okay. So you're going to plug in these values, verify that they are correct, and then obviously they're going to be normal. Please do verify it because you may get questions where one of them will not hold. And so in that case, you cannot use the normal model, okay? But it's very simple. It's just plugging in the values really. So the next problem should be more fun. Yes, so there's a lot of memorization this week. As you can see, there are quite a few formulas to memorize, but you have to memorize these two. These two conditions. And the best thing to do is just write it down, just write it down in your notes and then always refer to it. Remember that your final exam, you'll be able to use notes, whatever, it's open book. So you can use any notes anywhere. So it's really nice to put these down in a notebook and then always keep that notebook throughout this course. Okay. Okay, so now let me ask you, since we can use a normal model, what is my mu p hat, which is the mean of the normal distribution that we're going to use? What is that equal to? Very good. It's just 0.4, 40%. Whatever the p is given to you. How about the sigma p hat? What is that equal to? Nope. There's a formula involved. Very good. It's p times 1 minus p divided by n, and then the square root of the whole thing. Okay. So what is that? 0.40 times 1 minus 0.40, which is 0.60, divided by n, which is small n, which is 50. And then you take the square root of the whole thing. Okay, so now let's do that. We use Excel. This say is equal SQRT 0.40 times 0.60 divided by 50. And this is what I'm calculating here. You can see if I hit enter, I get 0.069. Can someone type this, please, in the chat box? I get, thank you, Angie, 0.06928. So this is my standard deviation. Standard deviation, mean. Are these steps clear? And then we have a few more problems. Okay, now excellent. Okay, now the problem says, what is the probability of obtaining 23 or more individuals with some characteristic? So 23. probability that X is greater than 23? Well, this is the same. This is the same as probability. What is 23 as a proportion of 50? 23 over 50. What is 23 over 50? Someone type that. And let's see if we match. I'm getting 46% or 0.46. So do you all agree with that? 23 divided by 50. Not 0.46, it's 0.46. Okay, so basically we were looking for proportion being 0.46. Now I didn't tell you, but actually the problem tells you this. See that? Problem says, what is the probability of obtaining X equals 23 or more individuals? That is, what is the probability that P hat is greater than or equal to 0.46? So this is what we're finding. This is what we're looking for. We're looking for this guy. Okay, so now let's find this in StatCrunch. I'm going to use StatCrunch. What is the mean? The mean is 0.40. So I'm going to change this to 0.40. What is the standard deviation that we found? 0.06928. And what is the value that we're looking for? 0.46 or more. So I'm going to put 0.46 or more. So I'm going to change this to greater sign. Did you follow all this, what I did here? So I hope you all followed that I put 0.40 here for the mean, 0.06928 for the standard deviation. I put 0.46 because that's what we're looking for. That's what the problem is asking you to do. And I get this answer, and this is the diagram. So let me know if you followed all this, and if not, I can maybe answer the questions. Again, in this case, remember, can you see how all we're doing is we're transforming the standard deviation, right? We don't do anything with the mean. We use whatever mean is given to us. Even in this problem, and even in the problems when we were calculating the means, right? All the means are going to be equal to the population mean. The standard deviation involves this transformation, okay? Yes, of course. Yes, Sandra. You're going to have to take a look at this a few more times, and then I'm sure you will be absolutely fine. Just go over these formulas a few more times. Obviously, the first time is not easy to get, okay? Yes, so StatCrunch, I said 0.40 is the mean, which is the original mean. Here's the transformed standard deviation that we calculated. And then the problem told you they want you to find P hat is greater than 0.46. Okay. Here's the answer. Now, similarly, the next problem says, what is the probability of obtaining 19 or fewer? 19 or fewer is the same as what is the probability that P hat is less than or equal to 0.38? Okay, 38%. So how do I do that? Yes, absolutely right. 19 over 50, which is 38%. So how do I do that? Less than 0.38. I'm going to change this to less than, and I'm just going to type 0.38 here. And you get this 0.3864. Okay, Cheryl is asking, so you have to figure out your new standard deviation. Yes, well, every time the problem is asking, you know, like in this case, absolutely. For proportions, yes, you always have to. Always have to transform the, well, in this case, you're not even given the standard deviation, right? You're not even given the standard deviation here. So yes, so all you were given was N, big N, and P. And then we used this data to find our mean and the standard deviation. and we assumed that we meet the conditions, these two conditions, to use the normal distribution. If these two conditions meet, then we can use this mean and this standard deviation as a normal distribution. Um, and then we can use this normal calculator to do our calculations. Okay, so I think this week's lecture, it will help to go over, the second lecture. It will help to go over one more time. And once just go over the lecture one more time and pause the recording, understand what's going on, and then um, so Erica, you can access these in your course Blackboard Shell. In the Blackboard Shell, you have a tab on the left side called Webinar Information. Okay, in the Webinar Information, if you scroll down, you'll see a course calendar where these are posted under the days they are held. There are recordings posted in the course calendar. Yes, it started at 9 p.m. just like yesterday. Okay. Any question? Otherwise, we're done for tonight. Sure, Maya. Thank you. These are two times a week. Next week, we're going to be meeting on Wednesday and Thursday. Sure, Kathleen. I'm happy to see that this is helping.